Welcome back. Welcome back. We're working on chapter 5. We're doing 5.1. We've already spent all of chapter 4 talking about triangles and how to say they're congruent to each other. Now we're going to be talking about different parts of triangles, things that happen when we start taking lines and putting them through angles and giving them names and looking at properties. You will see those triangle congruents show up again, so keep those in the back of your head. Without further ado, we're going to start with bisectors of triangles. And we've got some vocabulary that I'd like to go over first today. The first vocabulary word is the perpendicular bisector. We've already used that word several times. The word perpendicular means?
The two lines that intersect, or two lines that make a right angle.
Yep, two lines hit at a right angle. Very nicely done. And bisector means?
That they split it perfectly in half.
Yep, gets cut in half, perfectly in half. Gorgeous. So perpendicular bisector is a line that does both of those things. It's going to intersect some other line. It's going to do it at a 90-degree angle, and it's going to have cut it in half. Oh, that was a bad throw on my part.
So it creates two 45-degree angles?
No, it creates two 90-degree angles.
Oh.
Yeah, just like this. Yep. All right, so in a triangle, when we have a perpendicular bisector, it's a line segment, a ray. It could be a plane also. I know that's not listed, but it could also be a plane. And it's going to pass through the midpoint of the side and is also perpendicular to that side. Note, it doesn't have to pass through a vertex. Okay? Just like the example that I drew. In purple, you're going to see the word translated into Spanish. If you don't want to have the Spanish translation, you don't have to. But I found it in the book. I literally just went to the glossary of our textbook and grabbed these. The vocabulary word that isn't listed here, sorry, is angle bisector. It's a thing that cuts an angle into two pieces. We've got something called concurrent lines. Concurrent lines are going to be three or more lines that all intersect at some common point. Okay? So we've got three lines. They're coming together at one point. They're called concurrent lines. And the point at which they all run into each other at is called the point of concurrency. Okay? So that common intersection point of a whole bunch of lines, point of concurrency. Now we can draw perpendicular bisectors on the sides of a triangle. How many sides do triangles have? Three, which means how many perpendicular bisectors are we expecting? 3. Because if we have 3 sides, we can draw a perpendicular bisector at each side, and so we end up with 3 perpendicular bisectors. If I were to find the point of concurrency of those 3 perpendicular bisectors, I will have created the circumcenter of the triangle. And I did my very, very best when I drew that little diagram. I drew a triangle. I'm going to zoom in on that diagram. Sorry for those of you who are copying definitions. I'll zoom it back out in a second. But I'm going to zoom in real close to circumcenter, make it unblurry. There it is. So it's a little tiny triangle, and I did my very best to draw perpendicular bisectors, some lines that, some lines that hit at a 90-degree angle to the sides, but that break that side into 2 congruent pieces. Okay, can you see my attempt? And then where those 3 lines intersect and run into each other, I try to circle because it's kind of smooshy, is the circumcenter. Right? Confusion. All right. Let's try to clarify the confusion. I'm going to draw it again, okay? Yes? All right, so scooch that off to the side real quick. And all my markers. Okay, so I need a not blurry thing. Okay, so first off, I need a triangle, and I'll draw this triangle a little bigger so we can see it. So I need 3 straight sides to be a triangle. There's 1. There's 2 sides. Oh dear goodness. Okay. Okay, sort of. 3 sides. Yes? Now I'm going to draw the perpendicular bisector for each. And I'm going to guess where the midpoint is because I don't really know. I don't have the way to construct it here. So, YOLO, I think my midpoint is right about there. Going to get my right angulotron, the corner of my little hall passes here. Line it up with the point I said was the midpoint. And there's one perpendicular bisector. So far, so good? Second perpendicular bisector, I'm guessing is the midpoint right about here. Again, I'm just eyeballing it because we're just doing a quick sketch. And class is over. I'm kidding. They didn't intersect, but that's okay because I can always extend this one. All right, and now my last perpendicular bisector is going to again hit about the midpoint, YOLO, right about maybe there. And it's got to connect through to this point, and that should be about a right angle. Yep, it's a right angle. I did good. And so this point where they all crossed, that's the circumcenter. That's what we've named that point. And it's where all the perpendicular bisectors run into each other. In this diagram, it's not inside the triangle. It could end up being inside the triangle. Could be on one of the edges of the triangle. I don't know where it's going to be. Just wherever it happens to end up when you finish drawing it.
I don't get the difference between that one and that.
The difference between, give me the words.
Point of concurrency and circumcenter.
Oh, okay. So the difference between point of concurrency and circumcenter is just a matter of being more specific. A circumcenter is a point of concurrency. It is the point of concurrency for perpendicular bisectors of a triangle. Okay? So where point of concurrency would be like saying dude, right? Guy, as opposed to in. Incenter, if we do the same thing but with angle bisectors, we're going to end up creating the incenter of a triangle. And this one should always end up in the middle of the triangle somewhere. Okay, are we all right so far? Thinking face? Yeah, are we okay on the incenter? Yes, 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 yes. Yes, 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 yes. Okay, grab your phone, take a picture, zoom in, and if that doesn't help, then in a little bit I will hand you this paper and you can copy. Okay. Does that help, zooming it in? Yeah? Okay, you're welcome to do that. I did have a chance to check with Mom, so. Yeah. I'm going to root for the cool colored contacts for you. Note to self, try to edit that out. All right, let's look at some of our theorems. Can I cover up to concurrent lines?
Yes.
All right. Our first theorem is dealing with the perpendicular bisectors. We've got the perpendicular bisector theorem and its converse. The theorem says, if a point is sitting on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. Okay, so I have some segment A to B, and we have its bisector C to D. Okay, I'll zoom out again in a little bit if you're still copying definitions. So I have this segment AB, and I have this perpendicular bisector CD. If this point C is indeed on the perpendicular bisector, this distance between C and one endpoint has got to be the same as the distance here from C and the other endpoint. That's all the theorem is saying.
Yes.
Yes, sir.
What's the difference between a perpendicular bisector and perpendicular line?
The difference between a perpendicular bisector and just a perpendicular line is that the perpendicular bisector has to go through the midpoint of some segment. Whereas a line that's perpendicular, I don't care where it is, as long as it hits at a 90-degree angle. Whereas the perpendicular bisector has to both hit at a 90 and has to do it right at the midpoint of the segment. Yeah, any segment. Okay. The converse basically is just switching the order of things. So if we've got a point that we know is equidistant from the endpoints of a segment, then we could say that that particular point lies on the perpendicular bisector of that segment. So it allows us to go either way depending on what kind of information we're starting with. Since we've done all this work on perpendicular bisectors, when we get those to all intersect with each other and we create the circumcenter, it has a theorem. The Circumcenter Theorem says this. The perpendicular bisectors of the sides of a triangle are going to intersect at a point called the circumcenter. And this point is equidistant from the vertices, the corners of the triangle. Okay. I'm going to give you a second to finish the color coding and the highlighting, getting the words in. And then I'm going to zoom in on this figure. Great question. We forgot what equidistant meant. You're exactly right. That's exactly what it means. Equal distance. So that means that the circumcenter is going to be the same distance from every corner of the triangle. All right, so zooming in really close. The pink lines are your perpendicular bisectors. I didn't draw the whole thing because it would get messy. So we stopped at where the circumcenter was. So you see them all coming together, that really dark spot right in the middle? Okay? And we marked all these little sides congruent because they're bisectors. So all of these little sides of the triangle pieces are all congruent to each other. This circumcenter point then is equidistant to the vertices. So these lines that connect them out to the corners of the triangle are all going to be the same distance. They're all going to be congruent. I put a squiggle in there because when I start drawing these lines, I lose count after 3. So like one little line to show they're congruent, I can see 2 little lines to show they're congruent, not a problem. 3 little lines is starting to get confusing, but I'm okay. And beyond 3, I'm like, no. I don't know how many lines I've drawn. I'm confused. So I start using little squiggles. I've seen on some math texts that they put in numbers. So they'll write a number 4 or number 5 or so on. If you wanted to draw a little smiley face or a lion or a heart or just some sort of symbol that tells you every line that has that little symbol in it are all congruent to each other. And we'll be good. Okay, so develop your symbol, keep it consistent, everything should be happy. For me, you'll see the little squiggles for 4, and then I'll start numbering. Okay? I'll also be putting in colors because I like the rainbow. So far, so good? All right. I have 3 more theorems for you. Zoomy, zoomy, zoomy. I think that was a children's cartoon back in the day.
Team Umizumi.
Team Umizumi. There you go. I knew it was a cartoon. With yes, go right ahead. Is that a little better on being able to see it?
Yeah.
Yes. Okay. Note to self: bring a little lamp from home. We have the angle bisectors, which gives us the angle bisector theorem and its converse. And the angle bisector theorem reads this. If a point is on the bisector of an angle, then it's equidistant from the sides of the angle. And notice the picture. We're going to start with the angle, and we're going to put the angle bisector, the pink line that I've drawn. And I'm going to take lines from that point, and I'm going to make these lines perpendicular to the sides. And the moment I do that, those little perpendicular pieces are congruent to each other. Its converse reads this way. If a point inside the angle is equidistant from the sides of the angle, then it's on the bisector of the angle. Okay? This leads us to our Incenter theorem for triangles. The angle bisectors in a triangle all meet up at a point which we'll call the incenter. And this point is equidistant from the sides of the triangle. In a moment, I'll zoom in on that graphic. All right, there's the zoom in on the graphic. The pink lines are your angle bisectors. And then notice the incenter all has tiny little segments that come off it that are perpendicular to the sides. All of those little lines are going to have the same measure. They're all going to be congruent. Try not to get in the light. Okay? Yes? All right, let's do some examples. I've already got some done here, so let's just kind of chat about them real quick. Measure of FM. Let me grab a new page. Should I grab a new page?
Yes.
Yes.
Is this pretty much the same thing except with angles?
Yeah, basically. Okay, I'm going to turn off that for a second. Oh gosh, no, I want to turn off the flash not just leave it there. Off flash. Yeah, destroy my phone battery. There we go. Note to self, make more copies of this. All right. Here we go, fresh copy. Did you need these? Yes. Will you pass these back, please? To Miss Kelly. Thank you, thank you, thank you. Alrighty, so we're going to look at the measure. We're going to find the measure of FM. So here is segment FM. We're trying to find the measure of FM. What do you think?
2.8 because they're perpendicular bisection.
He's saying that FM is also 2.8 like this side. And then he said, because perpendicular bisector.
Yeah.
Which segment is a perpendicular bisector? FK is the perpendicular bisector for GM. And we have our theorem that states if a point is equidistant, sorry, I'm trying to find the theorems here so that I can read it to you. Oh, I passed it that way, that's all. If a point, which we're going to look at point F, is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Sure. The theorem states if a point is on the perpendicular bisector of a segment, then this point is equidistant from the endpoints of the segment.
The point F is equidistant to G.
And M. Exactly.
Is F KG, I mean FKF, I mean FKG, angle FKG, the same as angle FKM?
Yes.
Yes.
Also, that means they're both 90 degrees, because it's a perpendicular.
Exactly.
Wait. So are all the angles congruent? Because you have one top and one, and then the bottom one's half one.
Great question. The question was, does this mean all parts of these triangles are congruent? I have these sides congruent to each other.
Yeah, those angles.
I have those angles congruent to each other.
And those two sides
And
congruent.
this side congruent to this side because it's the same segment, which means the triangles are congruent by,
The side angle side,
yeah. That was in your head, he just read your mind.
or you can just do side.
Quit
side,
being a telepath, dude, and reading our minds. He's all frustrated now.
I'm tired.
You're tired. I'm sorry. Okay, let's look at this one. BD is the perpendicular bisector. Okay, So this is the perpendicular bisector. It's going to give me a 90-degree angle here. It's also going to do something for these segments. What does it do?
Make them congruent.
Perfect. Make their measures equal, which means this measure equals this measure, and I don't have to think about the algebra setup. I can just write that they are equal to each other. And then I can forget that I'm in geometry, and I can fall back to my algebra, and I can solve this thing for x.
And so x equals.
And what theorem was
Great question. The theorem, no, it's not a theorem. It is a definition of bisector. Because it being a bisector gives us that those sides were congruent. So it would be a definition. All right, I'd like to look at the ones on the very bottom. Let's start with IU. Okay. Right here, IU, this one. So I'm trying to find the measure of this segment. But to find the measure of that segment, I need to know the value of x, because I'm going to take x and then I'll multiply it by 7, and then I'll have my final answer. Yeah? Okay. What do I notice?
That the angle TRU and angle URI are congruent.
These angles are congruent. If those angles are congruent, what kind of line does that make ray RU?
And perpendicular. Wait.
An included line.
No. I had to think about that. It's definitely in the interior of the angle. You're not wrong. I liked where you were going with bisector, but not perpendicular because it's not 90.
Oh.
Is
So
19.
It's just a bisecting segment.
What's getting cut in half? A segment or an angle?
An angle bisector.
An angle's getting bisected, so it's an angle bisector.
And so we go to our angle bisector.
So we look at our angle bisector theorems, and one of our angle bisector theorems says if a point is on the bisector of an angle, and I have this point U that's on my bisector of an angle, then it is equidistant from the sides of the angle, which means this distance is the same as this distance. Which means
That 2x plus 5 is congruent to 7x.
equal to, because these are value numbers.
that you? Oh, wait, never mind. I'm trying to
Okay, you're not stupid.
No one's stupid here.
All right, gonna solve this equation for x. Here I go.
Thanks.
Yeah? All right.
They're both 7.
definition of bisector.
This would actually be angle bisector theorem. But we use the definition of angle bisector to get there. Angle bisector theorem. I can't write. That's supposed to be an R. All right, let's look at this one before we go on to our proof. All right, we want to find the measure of angle MYW. We want the measure of that angle. What do we notice?
That it is on the
They're
angle
both
bisector.
Oh wait, not the
How do you know they're on the angle bisector?
because
Hold
of
on.
the
Because
segment.
the-
No, the angle is congruent.
We don't know the angles are congruent
The
yet?
But because angle P and angle P and angle W are congruent, or at least the segments are.
The segments.
That's what you're going to say in the back, yeah?
And that means that if they're equal distance from each other, that means that it is probably the angle bisector because
What?
which
Well, it is the angle by
yeah,
These-
it is.
these segments are congruent and there's 90 degrees.
So it's
Which
perfect.
means
Sorry, what did we notice?
we notice that these segments are congruent and they hit it at 90 degrees. When we have that, that tells us that the distance right here from this point to this point are equal.
That means that's
We have
what it
equal
says.
distances, therefore M is on the angle bisector. That comes to us from the converse
Of the angle bisector.
of angle bisector. And because it's now on the angle bisector, this angle is congruent to this angle, and so we can set up our, bless you, algebra statement. Make sure I'm doing my algebra right, because I'm not writing out my steps.
See.
And that would
Yes.
be the angle bisector theorem.
Converse.
Oh.
Okay, now let's go to
The angle bisector theorem gives us the point on the bisector. The converse says if it's equidistant, then it's on the bisector. So one starts by telling us it's on the bisector and allows us to say it's equidistant. The other one starts with it being equidistant and allows us to say it's on the bisector. I'm moving on to the next page of notes. I'd like to look at the theorem on the bottom. Can I move the page?
Yes.
All right, this theorem right here on the bottom. All right, a little easier to see?
the first one is obviously the given.
Okay, the first one is obviously the given, he says.
Definition of angle bisector.
All right, I'm going to slow down a little bit. Work it out, and then see if we did a good job. All right, so the first one is given. Did we write all the stuff in the given? Yes. Okay, so we shouldn't need to write given again anywhere else. All right, then the next thing. I need my hands free, so I'm gonna. That is horrible. Oh, that's even worse. Okay, is that okay? Nope. 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 Okay, I was trying. Okay, I'll write like this. Okay, the next reason that we've been given is that we have an angle bisector. So we have to figure out where that angle bisector is. Okay, we're told that plane Z is an angle bisector for angle KJH. That means that's the angle that got bisected. So this would be the bisector because that's what's on the plane Z. And so this angle is congruent to this angle. And so those are the angles that the definition of that plane being an angle bisector are congruent. Yes? Okay. So I'm going to write those angles.
Angle HJM
HJM
is congruent to angle KJM.
Now notice that he made sure that the vertex was in the middle of the name. So J is the vertex of those angles. And so J is in the middle of the name. All right, the next thing that we have is that line segment JM is congruent to line segment JM.
Reflexive property.
Reflexive property, very nice.
Only thing I'm gonna get.
That's not the only thing you're going to get. You got given two, didn't you?
Yeah.
Yeah, so that's two things.
And also, S side angle side is a postulate, but I forgot to put that, so.
They forgot to put the postulate, you're right. So side angle side, what does side angle side give you?
Triangle HJM is congruent to triangle JMK.
You're absolutely right. It gives us triangles are congruent.
And then.
And then you were telling us which triangles they were. So can you repeat again which triangles they were?
Triangle
Triangle?
HJM is congruent to triangle JMK.
All right, when we're writing triangle congruence, we have to make sure that those corresponding parts are in the same order,
Oh,
okay? So if he stated HJM as our first triangle, which point corresponds with H?
K.
K. So then in my second triangle name, K has to be listed first.
JM.
All right? Good. Now that we have all of those congruent, are we allowed to say that the segments are congruent?
Yes, because of CPCTC.
CPC.
Congruent parts of a congruent triangle are congruent.
Corresponding parts of congruent triangles are congruent. In the previous step, we stated that this triangle was congruent to this triangle, and because this side corresponds to this side, they are congruent. That's all I had for you guys now. Thank you very much.
Every day, every day.
Oh,